we go. So today it should be an ideal lecture. I'm sorry, that's a horrible pun. I mean, we're lecturing on ideals today. We talk about ideals. What is an ideal, right? Mathematically speaking, of course, and why do we care about them? So we're hoping to ask and answer those questions today. So I'll start with a definition here. So this is my old lecture 22, ideals and factor rings. So definition, a sub RNG A of a ring. I said I wasn't going to talk about sub RNGs anymore. My bad. I can't avoid it. Of a ring R, all right, is called an ideal. An ideal if for every R in R and A in A, all right, both AR and RA are in A once more. All right. Oh, off the rim. I almost had it. We say it's a proper ideal if A is not equal to R. All right. And
for every R and R and A and R, both R and A are in A?
yep. So what this where I used to work, one of my fellow faculties, listen to me, one of my colleagues, usually people say, would refer to this this right here is what he would refer to this as uber closure. Because basically, like, here's a picture of it, right? Here's A, right? And if you multiply, R on it, it goes back to it A, right? And that has to happen both on the left and the right, Uber closure. And I know it's kind of off-putting at the start because you're kind of expecting it to be what, like there's an asymmetry, like R here, but yeah, this is what's needed. And what does it take? What's the subring test, by the way? Reminder, just a reminder. If A comma B in A, right, a subset of R implies what? It implies AB and A plus or minus B is in A again. That makes A sub RNG. What's the difference between a sub RNG and a subring? I mean, every subring is a sub RNG, right?
Yeah.
But what happens if you have a subring which is an ideal? Let's think about it. What if ideal A is a subring? So remember then I, right? Well, the number 1, let's say, is our notation for it. Then 1's an element of A, right? Because it's a subring. But then what else? But r times 1 equals to r is an element of A, right? For all r in R by the Uber closure. I can take any element in the ring, multiply it by something in A, in this case 1.
So A is equal to R?
So A equals R, right? Thus, A is equal to R. So you cannot have a proper ideal which contains the identity. If you contain the multiplicative entity of the ring, you get everything if it's an ideal by the Uber closure. It is nice to have a name for it, and I like Uber closure as a name.
Can we talk about ideals in like other courses? Like I feel like this is like a property of matrices, maybe that we might have.
No, I don't think we've talked about ideal here, as far as I can think of, not in one of the courses I've had with you.
I'm talking about like just in general. Like are there certain like linear groups, matrices that follow kind of this structure?
Well, you can find an ideal of a matrix ring, but do all of them? No. Certain ones do. Like I think, I'm trying to think. I think like, oh, I don't remember right offhand. I don't have sorry. Okay, so theorem. Here it is. A non-empty a subset of a ring R is an ideal of R if you have the following two criteria satisfied. Number one, AB in A implies that A minus B is an element of A. And 2, Uber closure. A in A and R in R implies AR in RA, an element of A. So if you're closed under subtraction and also Uber closure, you get an ideal, right? And the proof, I won't even really write down. It's just kind of obvious. So notice that Uber closure automatically gives you like closure under multiplication. So you get closure under multiplication and you get subtraction. Actually, you don't even need a plus here, like subtraction. I mean, this is true, but the minus being there is what you need for the subring test, if I remember right, subring test. So anyway, this is pretty much immediate from the sub-RNG test. And of course, this is the extra thing you need, Uber closure, to get an ideal. So anyway, this is not like a deep theorem. This is just like, here's how we can check something's an ideal. Okay, so just as a calculational sort of benchmark there. So what are two sort of stupid examples of rings? Any ring R? If we have R a ring, then A equals to R, and A equals to just the set containing, I think it's just 0. Yeah, just 0. So you can easily check that conditions 1 and 2, these are non-empty, right? If the ring is not the empty set, and R is not the empty set, okay? So clearly these two conditions are met for the whole ring and just the set containing 0. Because 0 times anything, remember, is 0 again, right? So these, of course, this is the trivial ideal, right? The trivial ideal. And this is the what? The improper ideal, I guess you could call it, right? So, example 2. Here's where we have already been talking about ideals, okay? So if we take the ring to be the integers, right? R equal to the integers, then you can take A equal to n times Z. Okay? And so if we have, let's see here, let A and B be an element of NZ, that means what? A is equal to like NJ, and B is equal to NK for J and K in the integers, right? And then you can check it out, right? Like A minus B is, well, NJ minus BK, which is, NK, N times J minus K, which of course is an element of NZ, right? So condition 1 is met. It's non-empty. What else do we need to check? We need to check Uber closure, right? So to check Uber closure, if, let's say X is an element of Z, then XA is what? I should use R, my bad, just to stick with the definition. I don't know why I'm using X, R. Then RA is, of course, equal to RNJ, which is N times RJ, right? Which, by the way, is equal to, AR, because things commute here, and that's an element of NZ, right? So therefore, conditions 1 and 2 met. NZ is ideal of Z. All right. Very good. So next up, next definition here. This one's an important one. This will be with us for the rest of the semester. Let R be commutative ring with unity 1, all right? And, let A be an element of the ring, all right? Then we denote the principal ideal generated by A as bracket A bracket, right? And what that means, bracket A, it's equal to AR such that R is an element of the ring, right? And other notation you could use for that, it's really just A times the ring, and of course that's also equal to the ring times A because we're assuming commutative. So, like, obviously, as a tacked-on comment to our last example, notice A here is the principal ideal generated by N. That is literally NZ, which of course is also equal to Zn. Yeah. All right. Theorem. The principal ideal generated by A is an ideal. So the conditions of the theorem are the ones that are stated in the definition, all right? We're a commutative ring with identity. So you're like, well, you just called it an ideal. Doesn't it have to be an ideal? Well, just naming something an ideal doesn't prove it's an ideal, does it? It's just a name. Ideally? Oh no. That's horrible. But I'll allow it. Okay, so let's let X and Y be elements of principal ideal generated by A, right? Then there exists, let's say, R1 and R2 in R, such that what? X equals to, let's say, R1A, and Y is equal to R2A, right? And if we look at Y minus X, what do we get? We get R1A minus R2A, which is R1 minus R2A, which of course is an element of the principal ideal generated by A. So we have condition 1 met for the ideal test, right? Closure under subtraction. If R is an element of R, then Rx is what? Well, that's equal to R1A, right? Which is equal to, which is again an element of A, as R1 is an element of R, since R a ring. So we took an element of the ideal, in this case X, we multiplied it by an arbitrary ring element, in this case R, and we show that it's again in the principal ideal generated by A. So indeed, the principal ideal is an ideal, since we have met conditions 1 and 2 of the ideal test, right? Okay. What are other examples of ideals? There are many. So, example, I don't know what example I'm on, 3? It's debatable. 3. This is actually, just to let you know where I am, 4.2.8, page 130, if you're following along at home. Anyway, so consider the ring of polynomials with real coefficients, R bracket X. So this is polynomials with real coefficients. Then what is this thing? What does that mean? That means X times f of X, right? Such that f of X is what? A polynomial with real coefficients. So what is that? I mean, if you want me to, I could be a little bit more explicit. What does an arbitrary polynomial look like? Sometimes it's helpful to just kind of, get into the details here. So like that's an x to the n plus plus a1x plus a0, right? And when you multiply that through by x, what do you got? You got like, I'll start it at the a0 term, a0x plus a1x squared plus plus an x to the n plus 1, right? Such that the a0 all the way out to an are real numbers. So that's what this is. Can you put it in other terms? What is the ideal generated by X? It's a set of polynomials with what? With trivial constant term, right? So that's what that is. I think there's a typo in my notes in the next example. I have written bracket X where I meant to write bracket XY, I believe. So you can also look at the ring R of XY is ring. So this is the ring of bivariate polynomials. So it includes like sums of, powers of x and y. Yeah. And so in this, you can look at the ideal generated by xy. All right. And so here, as an example, is an ideal. And so here's something. I give this example just to give you a sense of what's not in that ideal. If you look at f of xy is, say, y plus y cubed plus x squared y squared, right? Well, that would be an element of this ring, right? But f is not an element of the ideal generated by xy, right? So like the ideal generated by xy has to be multiples of xy, essentially. Xy times something else. So it's got to have, xy in there. In contrast, like x squared y squared, which of course is what? Xy times xy, right? That would be an element of this gun, of this ideal, because it's a multiple of xy, right? Now, if you can build an ideal from one thing, you can also build an ideal from more things. So we define, and so this is much akin to the concept of span in linear algebra. So in some sense, like just one thing is kind of like a span of a single vector, right? It's the r multiples of a single vector, if you want to think of it that way. I mean, don't do that. It's not that, but it's like that. So here's a1, a2, an. That is the set of r linear combinations of the form a1r1, a2r2, an/rn, such that r1, r2, rn are in the ring. So that's the ideal generated by a1, a2, an. A principal ideal, just one generator, right? So it is a interesting and sometimes non-trivial question to ask whether, if you have an ideal generated by more than one thing, can it be rewritten as a principal ideal? Maybe, maybe not, This does become linear algebra if we do what? So if you take the case, say the ring is equal to the real numbers, I mean, that is a possibility. That's a ring, right? And I guess I need to take, like, say r cross r just to keep it more interesting. So the real numbers cross the real numbers. Ah, curses, it's not quite right. It's not quite right. No, it's not quite right for the span. Because the difference with linear algebra, when we take a span, what's it look like? What's the difference in the structure? Yeah, in linear, if I have something like the span of vectors 1, 2 through n, right? Then that is, yeah, it's C1, V1, Cn, Vn, such that the C1 through n, and let's suppose we're looking at a real vector space, okay? Those are real scalars, but notice, but V1, V2, Vn, these are elements of the vector space V, right? And the vector space V, it doesn't have to be, there's a relation here. Notice that both the A sub I and the R sub I, they're all elements of the ring R, right? See the difference? In the principal, in this ideal generated by A1 through AN, the things we're multiplying, the A1 through AN, are on the same sort of structure level, if you will. They're both from the ring. In contrast, in linear algebra, when I take a span of vectors, while the formula looks the same, it's actually quite different because these vectors are different objects than the scalars, right? The scalars are taken from a field. The vectors could be 3-dimensional vectors, 4-dimensional vectors. They could be a lot of different things, right? So there are similarities, but there are also differences. So example 4.2.13, I have the set of functions from R to R, right? We talked about that. So this is just real valued functions of a real variable. And I point out that if you look at if you say, C, let's say C1 R is equal to set of once differentiable functions. Right? Well, if you take F, and let's call that A, and let's call this R, all right? So if you take F and G in A, then F minus G prime is F prime minus G prime, right? And by the rules of calculus, the derivative of the difference exists, and so that implies that F minus G is in the ring, right? But what about if you take H, a function, and then you take H times F, right? Well, then H times F prime need not exist, because the ring is all functions, right? So if you multiply that by something that doesn't, let's see, for example, we could take F equal to 1 and H equal to the absolute value function, right? Then HF of x equals absolute value of x, right? And the derivative is not existing at 0. So therefore, HF is not an element of A, and so we fail Uber closure, right? So the set of differentiable functions is an example of a subring, all right, which is nevertheless not an ideal. All right. Oh, I also give the right before that, the example before that, I looked at the ideal generated by x and 2. Right? And so basically that's things of the form x times h of x plus 2 times j of x, such that in this case, the ring here was zx, polynomials with integer coefficients. So if you look at that for a second, that's going to be the set of polynomials. Well, look at the constant terms. Like, what happens with the constant terms? The constant terms are necessarily even in this thing. And beyond that, it's anybody's bet, but the constant terms have to be even. So it's kind of a nice example. Here's the main event, proof-wise, for today. Well, I say that's not actually quite accurate. Hopefully I'll get further. Let me not let this proof drag out too long, actually. So here's the theorem. Let R be ring, and a sub RNG, all right, of R, then define the set of cosets R mod A, if you will, equal to, and these are additive cosets, R plus A, such that R is an R. All right. The following possible operations. And so here we go. Possible operations, S plus A plus T plus A equal to S plus T plus A. In other words, to add the cosets, you add the representatives of said cosets, and multiplying S plus A times T plus A is equal to ST plus A. All right. For each S and T and R. Right. Then, here's the claim. R mod A forms a ring with respect to the above operations if and only if A is an ideal. In this case, we call this the factor ring of R by A. All right, so anytime you claim something is a operation on a set of cosets, it begs the question of, like, is it well defined, right? So the first thing we have to address is this actually an operation? So the proof, let's see here, it goes in a few stages. Suppose that S1 plus A is equal to S2 plus A, and T1 plus A is equal to T2 plus A, right? What does that mean? Then what that means then is that well, it means that it means a lot of different things, but one clear, fruit fly. You can get from this that S2 minus S1 is an element of A, and T2 minus T1 has to be an element of A. So I think I'm jumping let me try to explain to you why I don't have to prove all of that right here. And it's because I've forgotten something I should say at the start of this proof, which is pretty simple. But notice the following. If A is a subring, let me put it in red. If A is a subring, that means that as an additive subgroup, I'll just write this, A sub RNG is additive subgroup of R. Therefore, A is normal subgroup of R. So I don't know if you guys did in your abstract algebra or not. Did you talk about like factor groups and normal subgroups? If you did factor group, you had to do normal subgroup. Normal subgroup, so like in group theory, typically we say H is a normal subgroup of G.
Yeah, we did that.
That means that it's closed under like conjugation, among other things, right? So a normal subgroup. Another way to look at it, of course, is that the left and the right cosets are equal for a normal subgroup. The thing is, this isn't what it looks like in our current context. It looks like this. And it's an additive subgroup, so it's automatically normal. It's the thing, the left and the right cosets are equal because it's a commutative operation. So what all of this means is that already we know that the set of cosets can be thought of as a factor group with respect to the additive structure. All right, and when we studied additive cosets, we learned, among other things, that they're equal only if the difference of the elements is in the set, right? So this actually, we have proved this in our discussion of factor groups in the previous course. Now, if you don't believe me, prove it that it's true. You can prove that the only way that these cosets are equal is if their difference of the representatives is in the ideal in this case, all right? Okay, so what? Then this means that there exists A1 and A2 such that what? Such that S2 minus S1 is equal to A1 and S2 minus T2 minus T1 is equal to A2, right? That is, S2 is equal to S1 plus A1, and T2 is T1 plus A2, right? So check it out. If we have S2 plus A, right, plus T2 plus A, I'd like to show that this is equal to S1 plus A plus T1 plus A. That will show that the operation is independent of my choice of representatives, right? It will show that the operation of addition is well-defined. And I think I actually already know the addition is well-defined here because this was the definition of addition in group theory, but I'm rehashing some old arguments here, admittedly. So that is equal to what? Well, that's equal to S1 plus A1, right? Plus A. Excuse me, my bad. So by definition, that's S2 plus T2, right? Plus A, but then I can put in, what is S2 plus T2? Well, it's S1 plus A1 plus T1 plus A2 plus A, which then the thing is, by the rules of coset calculation, you can absorb elements of the coset into the coset, right? Like into the, you can absorb elements of A into A, is the way this works, this calculation, So this guy and this guy, they get sucked into that. And this is just equal to S1 plus T1 plus A, right? And that shows you that the addition is well defined. It didn't matter whether I used, finally, S1 plus A, T1 plus A, right? So it didn't matter whether I used the one representatives or the two representatives, either lead to the same result, right? The addition is independent of representative. And actually, I didn't need to prove that. That was already known to us from group theory because this is a result about factor groups, additive factor groups. But the multiplication thing right here, that actually we need to prove because that's new. So let's work on that for a second here. Let's see here. So I'll probably make a homework that refreshes your memory about why cosets are equal, just to have you work through the things, just to make sure you guys are on the same page with me. There's some easy homeworks to assign there, after your test 2, of course. Let's see here. So I wanted to check on S2 plus A times T2 plus A. I'd like to show that's the same if I replace it with 1s instead of 2s, yeah? So this is, by definition, S2 T2 S2, T2. Sounds like it could have been a robot in Star Wars, but missed out. S2, T2. And then what? So then I'll just remember what we had. We can trade S2 for what was it? S1 plus A1. And T2 is T1 plus A2. And it basically all goes back to this fundamental lemma that multiples like, well, actually, this is where uber closure matters. We'll see in just a second here. S1, T1, right, plus A1, T1, plus S1, A2, plus A1, A2, plus A. But the thing is, notice that everything here, this is an element of A by uber closure. Well, that's the thing. If A is an ideal, right? If we have uber closure, then all that stuff gets sucked into A, and we're just left with what? S1, T1 plus A. Which, of course, then we can unwrap like so, and then we've shown what? Multiplication is well defined. It's independent of the representative. Now, does that prove that does this prove that R mod A forms a ring? No. At the moment, all we've done is given evidence that if A is an ideal, right, then R mod A is at least a set with two operations on it, namely addition and multiplication. It still remains to prove what? That those operations satisfy the axioms of a ring. So you got lots to check, right? Lots and lots to check. It remains to show if A is an ideal, then R mod A forms ring. Now, in the notes, I have some of those things. I'll just mostly focus on this one here. For example, notice, and this is actually important to our understanding, 1 plus A, right? 1 plus A times R plus A, how's that work? Well, that's 1 times R plus A by definition, right? And so that's R plus A again, right? So it appears to me that the 1, if you will, for the factor ring is equal to the 1 of the ring plus A. So there is a multiplicative identity. So what I'm saying is the multiplicative identity of R mod A is 1 plus A. Here's why. Right. Now, what are the other axioms we have to check? We have to check that the addition is commutative. We have to check that the multiplication is associative. We have to check that we have the left and right distributive properties. All right. So I'll let you read the notes. I have them written there. The proofs are pretty straightforward. And I think I have omitted one of the distributive laws, which I'll probably make you do homework. So what I'm trying to say is proving the rest of the laws for the factor group are pretty straightforward. All right. The thing maybe I should talk a little bit about is I claimed if and only if, right? So what would it mean for A not to be an ideal? See, if A is not an ideal, then either how can I say this? There exists A and R such that AR is not an element of A, or RA is not an element of A, right? Then what happens what happens to this, the well-defined argument for the operation then? See, what happens is you're not able to throw out the A1T1 or the S1A2 term in this context, right? So this implies that the multiplication not well defined. And if the multiplication is not well defined, it's not going to give you a factor ring. So uber closure is necessary for the multiplication to be well defined is the key. All right, so let's look at an example. What example am I on? I don't know. Well, it's 4.2.15 anyway. So I have the ring equal to the integers and the ideal equal to 3z, all right? Then the set of cosets, it includes 3z, 1 plus 3z, and 2 plus 3z. Them's your cosets, right? And if you, for example, I'll just do one of them. I'll do multiplication. So you've got your 3z plus 1. Oops. I'm trying to write. I mean, it doesn't matter. I'm just trying to be consistent. Right? So you tell me how we multiply these, how's it go? Well, 3z times, so 3z times 3z gives me 3z, I believe. And this gives me 3z. And this gives me 3z. And likewise, 3z, 3z. Right, because 3z is, what is 3z here, by the way? Yeah, I think the thing I failed to make a mention of over here, and I should have, is likewise 0 for the ring is equal to 0 plus a, which is just a. So the ideal itself serves as the 0 for the factor ring. A good intuition for what a factor ring is you're redefining 0 to be everything in the ideal. The whole idea really is to squash everything in the ideal down to 0. That's really what we're doing. So in this example, 3z is 0. So like 0 times anything is 0 again, right? And in contrast, 1 times 1 is 1. 2 times 1 is, 1 times 2 is 2. And still, and 2 times 2 is 4. 4 plus 3z, though, is equal to 1 plus 3 plus 3z, right? And so that, you can eat it, 1 plus 3z. Of course, this whole method of calculation I'm doing right now is very familiar, isn't it?
Yeah, it looks like algebra.
Exactly. This is the same table as if we do multiplication for what we've before called z sub 3, right? 0, 1, 2, 0, 1, 2, 0, 0, 0, 0, 0. 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. 2 times 2 is 1. Of course, so what I'm trying to tell you is that whether you look at z3 or if you look at z mod 3z, these are really just two different notations for the same animal, right? These are isomorphic. And so I would say probably a good viewpoint to take is that this is really just a shorthand for that, right? So, and this is not unique to 3, right? Generically speaking, z the residue classes mod n really is just the factor ring of Z mod nz, right? Now, we didn't say that earlier because we didn't know what a factor ring was, right? So I'd encourage you to look at examples 16 and 17. I will, 16 is actually a matrix example like you wanted. And so what it is I don't want to get into all the details of that example, but I'll just mention briefly what it is. So there, the ring is 2 by 2 integer matrices, right? And the A is just, it's just even 2 by 2 matrices, all right? And you can prove that A is an ideal. So this is actually an ideal. And that's kind of neat because when you look at the factor ring, R mod A, this is a matrix ring with 16 elements. And I have them listed, sort of. All right. What's more interesting, though, is the next example, because it takes us back to Gaussian integers. All right, so if we let the ring be Gaussian integers, all right, so Z adjoin I, right, then we can look at A equal to the principal ideal generated by 2 minus I. So how does that work? So I say keynote. Key thing to note is 2 plus the ideal generated by 2 minus I is equal to I plus the ideal generated by 2 minus I. Now the reason for that is that 2 minus I is an element of 2 minus I, right? I mean, the thing above is true because 2 minus I is an element of the ideal, right? If you have the principal ideal generated by something, that something, whatever it is in that principal ideal. Okay? So this is true because of that. So if you have something, right, if you have like A plus BI plus the ideal generated by 2 minus I, what can you reduce that to if you think about this?
Well, that was 2 is like 2, 0 I, right? And then I is 0, 1. So could you change this to
Yeah, I said like the way to think about this is for cosets, 2 is equal to I. The way that Conrad would say that is mod the ideal generated by 2 minus I. That's the section we skipped in Conrad's blurb on Gaussian integers, actually.
okay, so
But
A plus BI would just be either A or B.
so it's like A plus
Yeah.
2B, right?
Yeah.
But, well, anyway, I don't, honestly, I wish I had a more clear-minded explanation to you for the algorithm of figuring this out. But let me just say, after some calculation, you can convince yourself that there are the following things. There's the principal ideal generated by 2 minus I itself. There is 1 plus that. All right, there is 2 plus that. And there is 2 plus I plus that. And then there is, finally, 1 plus I plus that, which you could also write as 3 plus that, plus the ideal. Now, I color-coded those as blue, green, red, yellow, and pink in dots of a picture I made, which I will not attempt to reproduce on the blackboard at the moment. But if you look here on page, and my notes are also black and white, so it's not any help, but page, what am I on? Page 133. I've made a picture of sort of like the fundamental cell here. See here, how to think about this. I mean, one way to think about it is in the Gaussian plane, you've got the origin, and I've got 2 minus I is like over here, right? And if I multiply that by I, it gives me, you know, like this. And if I add these two things together, it gives me that. So this is sort of like fundamental region defined by 2 minus I. And if you look inside that rectangle, you'll find the things I've listed, namely 0, 1, 2, up here is 1 plus I, and here's 2 plus I. And I don't need to include like the other things because they're already included as coset representatives. You see what I'm talking about? Like 0 would be like let's see here. So 2 minus I is already represented by 0, right? So I don't need that for a representative. So, and then let's see here. Up here is I times 2 minus I. So that's also just I times 0. So that's still 0. That's also 0. This one's still 0, right? And 0 plus 0, well, over here, so these are all 0 in terms of like, if I use these numbers plus the coset, I get the 0, I get the you know, just the principal ideal generated by 2 minus I, right? And so you start thinking through this. If you look at the fundamental region and you find distinct points in there, those have to be the fundamental representatives, because if you keep going past that, you're just going to be able to get new points by adding copies of what you already have, and those things collapse into the, anyway. So I didn't prove it, but that's kind of a sketch of what's going on here. And the next example, I think, is even more interesting. So the next example, 4.2.18, here I have the ring of real polynomials, and the ideal is the principal ideal generated by x squared plus 1. So what this means is that, right, is that in R mod A, x squared plus 1 is like 0. I could say mod x squared plus 1 if you want to use that kind of language. But let me be more specific. What I'm saying is that x squared plus this ideal is equal to minus 1 plus the ideal, right? Because this is true because x squared plus 1 is an element of the ideal generated by x squared plus 1, right? So this gives us license to simplify x squared and replace it